Started in just a second. I apologize for the delay.
And he just started drawing my diagrams a lot bigger.
Yeah. That problem wasn't too bad once you get it. I don't remember. I have to remember that negative shit. So.
Oh yeah.
Negative derivatives.
Anyone computer come up here a second ago?
Yeah. I saw something.
Yeah.
Because I think I did mention it. They did. I like that they're well, one of them was like identical. Yeah, that's not good.
Okay, we'll be doing some icebreaker questions today. I'm Dr. Mickelson. I borrowed some of these slides from my 2B class, which is why there's electricity all of them, and this class is not about electricity. This is me. You don't have to go into a lot of details since you're only going to be stuck with me for 3 days. I was an electrical engineer first. I was an engineer for 25 years or so. I was always interested in physics. I came back to this very young West University. I got my PhD 3 years ago here in physics doing lunar laser ranging with Dr. Murphy. We trace out the orbit of the moon around the Earth to within 1 millimeter, right? The thickness of a dime. Very accurate work. We do that as a test of gravity. I have a book on quantum mechanics that will be out in the next couple of months, published by Springer. And I'm an all-around great guy. Any questions? Normally I would ask who you all were, but in the interest of time, I'm sure Dr. Carr already did all that stuff. Just for my class, I would want to get to know you better. It's stuff that I don't want to get to know you. I just feel obligated to meet Dr. Carr's requirements here. I usually use every minute of class time. I apologize for being late now, but we will end at 9:50 on time. Please stop me during this class, anytime, if you have a question, anytime. If you raise your hand and I don't see you, which can happen because right now I'm blinded by this enormous light in my face, then just call out. Say, excuse me, professor, whatever, so that I'll hear you, and then I'll take your question, okay? Smart people ask questions. Right? That's what it is. Okay? Smart people ask questions. My classroom is a place for questions and learning. It's a safe place for questions and learning, and I take that very seriously. Every question you ask is a good question. Okay? The office hour this week will be at the regular time, but my office is right around from Dr. Carr's. If it's too crowded there, we'll move into one of the conference rooms. I'm on the north hallway, conveniently located right next to the men's room. And I give my thanks to Evan Gross, who taught 2A in the summer and gave me some information on this. We'll start out with a review of some of the stuff that Dr. Carr already talked about today, and I'll give some more examples as was requested and go into some details. And then I hope we'll have time to move on to momentum, but the key is not to meet a time schedule, the key is to meet your understanding schedule. Okay, so if we run late and we don't start momentum till next time, then so be it. Okay? Any questions? Okay. So work. Anybody know who this is? That's so funny.
A band?
It's men at work. It's a band. They used to exist. So work can be thought of as the process of converting energy from one form to the other. There are different kinds of work. There can be thermodynamic work. There can be electromagnetic work that's done. There can be mechanical work, force times distance. So there can be different forms of work, but work is quantified. And because it is the process of converting energy from one form to another, it's quantified in units of energy. How much work, how much energy you convert from one form to another. And what is the unit of energy?
Joules?
The joules. Oh, you guys are good. Usually nobody wants to answer that. Forces can do work. So I'm going to give a lot of the formulas in both the one-dimensional and three-dimensional form, because sometimes the one-dimensional form is a little bit simpler to understand in terms of the concept, and then you extend that concept into three dimensions. So we'll look at a couple of one-dimensional and two-dimensional details here. But in one dimension, so a particle is just moving along one coordinate. The work is given by the integral of the work done by a force is given by the integral of that force over x. And I should say that in general, this f can be a function of x. So I really should have written this as f of x. I mean, it's possible that the force is a constant as well, and that's fine. But in general, it could be a function of position x, which is why we have to do the integral, right? Because if it were a constant all the time, we would just pull it out of the integral. And we wouldn't need to, and then we would have the integral of dx, which is trivial, and we wouldn't have to actually integrate it. So is that clear? Now, in three dimensions, it's a little bit more complicated because now our position is a vector r, a three-dimensional vector. It's a point in space. And we have some force field. A force field, a field in mathematics, one of the definitions of a field is it's a function of space. And a force field is actually a vector value function of space. At every point in space, there is a force vector associated with it. That is the force field that we write f of r. And being a vector, we can take a dot product with a small three-dimensional displacement in space, which is dr, a little tiny incremental movement in space. And the dot product, geometrically, what's a dot product? Without using the word cosine, what's a dot product? What'd you say? It's a projection. It's the product of the projection of one vector onto another. The projection, the amplitudes, the parallel components. It's the product of the parallel components of two vectors. And it's a number, it's not a vector, because it's just the product of the parallel components. It has no direction associated with it. So work is a number. It comes from two vectors, but it's a number. Question? Okay. I'm assuming this is review, so I'm going a little fast, but I just want to get us started on the same page. So let us now consider some kind of static force field, where I'm using the word static loosely. And what I mean by that is it defines a force vector at each point in space, f of r, that's the definition of a force field, it's a force function of space. And then it takes no outside energy to create this field. So we might have a fixed electric charge that isn't moving, and it just sits there, and it'll sit there forever, and it doesn't take any energy to keep that charge sitting there, right? Or maybe we have a planet, like the one underneath me, and it just sits here, and it exerts a gravitational force all the time, but I don't have to put energy into it to get the gravity force, right? The Earth doesn't run down and gravity gets weaker and weaker. Like, it just stays here forever, okay? So that's what I mean by a static force field, something that can just sit there forever, that doesn't require me to run a generator or plug into a battery or anything, okay? So examples would be gravity, an electric field, as I already mentioned, and a spring, right? I can compress a spring, and then it exerts a force, and so and the more I compress it, the greater the force. So the force is a function of the compression or the position of the end. The force is a function of position. It's a force field. But I can leave a spring compressed forever and it stays compressed and it always exerts that force, and I don't have to plug it in to make it be a spring, it just is. Okay, so that's the kind of force field we're going to consider right now. And the question is it conservative? And so two of the questions we can ask to help us decide that. First of all, why do we even care? Trust me on this for a minute, and we'll go into it in more detail, but it turns out that these important forces are in fact conservative, and that's an extremely useful property. And it allows us to do a lot of things that would be much, much harder if we didn't know that they were conservative. So does it allow me to get endless energy from it? Like, can I compress a spring once and then run my car forever on this spring because I compressed it once? Well, no. I mean, I might connect the spring up to my wheels and it'll move my car forward once, and then the spring expands, and that's it. It's gone. So a conservative force is one that, because it is self-contained, it has no external energy source, it can't just sit there and create energy forever out of nothing. I mean, it'd be totally awesome if we could get energy forever out of nothing. It would solve a lot of problems, but the universe doesn't work that way. And the second is, does it have a potential energy? And again, that's a little bit more advanced concept. It's a scalar field, a scalar function of space, and we'll see that conservative force fields have potential energy. And we'll go review again the relationship between the two that I know Dr. Carr did on Monday. So here's an eye-clicker question for you. Oh, no, it's not an eye-clicker question. But there will be eye-clicker questions shortly. Do objects always move in the direction of force applied to them? No! Great! I love it. You guys are great. Here's a battery. Which way is the force of gravity? If I move it over here, which way is the force of gravity? If I throw it like this, does it move in the direction of the force? No. Does it bend toward the direction of the force? Yeah. Okay. Good job. Sorry, I'm not trying to make fun of you. I'm just saying that's a big concept for a lot of people. And so I'm pleased that you guys are so up on top of it. So here's the example. You hit a baseball across the field. It's like a battery from the ground. The force is gravity. So we can draw lines of force that sort of look like this. I mean, that they are, what is the gravitational force here? What is the gravitational force there? What is it here? And they're all the same because gravity for small heights above the Earth is pretty much a constant. But of course, the baseball is moving across the lines of force, and it's not moving in the direction of the lines of force. It's got its own momentum, that we'll talk about in more detail, that carries it across the lines of force. But it does accelerate in the direction of the lines of force. That's what forces do. They accelerate masses. Right? That's the definition of force, F equals ma. And so it does bend in the direction toward the lines of force. Now we have a bigger question. So imagine we have one of these static self-contained force fields that I don't have to plug into the wall. And it's a function of space. In this case, we could say it's a two-dimensional function of space, because that's all we need for this question. We have some particle on which the force field exerts its force. And now we can move this particle from point A to point B. I've tried to copy the notation in the book. By the way, I think the book's discussion of this whole subject of potential energy is honestly seriously lacking. And so I'm hoping that this will help to plug some of the holes there. So how does the work done by some force on a particle, moving it from A to B, I accidentally left them capital up there, but it's supposed to be little a and little b. Compare if I move the particle along path 1 compared to path 2. Okay? So I will start this. I'll give you a 5-second notice. So you can click in with your answer, just like I did, just like Dr. Carr gave you a 5-second notice. I can see the number of answers popping up, so can you. You'll see the little bar chart. Think about it for a minute. Think about the principles we just talked about. Right? And I use the popcorn method for when to stop. Right? When you hear the kernels are popping really slowly, it means they're almost all popped. And then this is when you take it out of the microwave. Okay, so when you guys are mostly popped, then we'll stop. Okay, 5 seconds. Usually there's a big flurry of pops right after I say 5 seconds. So once again, you guys decide. my expectations. So, most people say it's the same, a few people say it's less along path 1. So let's explore that for a second. Why would it be less along path 1? Let me move this out of the way so you can see it. How about the path length along path 1? How does that compare to path 2? It's shorter.
But it might make a difference because ultimately we're working against a conservative force field. Therefore, the path shouldn't make a difference.
So he says, but we're working against a conservative force, so the path shouldn't make a difference. So that may be true as well. One thing you notice is along path 1, the force and the little displacement vectors, dr, are almost always parallel to each other, or very close to parallel. And so what does that mean about the dot product of those two vectors? It's what?
The angle is 0, therefore it's x dot r.
Right, the angle is close to 0, and so it's pretty much the product of the magnitudes of the vectors, because they're almost parallel all the time. It's the maximum dot product I could get. 0 angle is when they're both parallel. And along path 2, though, look at this. Wow, a lot of these DRs are substantially different than the force vector. And so what is that? How does that affect the dot product? It gets smaller. And so it could be that the amount smaller of the dot product along this longer path, it could be that that's exactly enough to make it equal the same amount of work to path 1. I mean, it could be, but I didn't show it. So it could not be, too. So, final check then. If I take a particle from along some path from A to B, and the force field does some work on that particle, what happens? How much work is done if I go backwards along the exact same path? How does the work going backwards compare to the work going forward?
Negative.
It's the negative. So now imagine if the work along path 1 and path 2 were different. Let's just say path 1 is bigger, but the argument would work either way. But for definiteness, let's assume that the work done on path 1 is bigger, and the work done on path 2 is smaller. So I could let my particle move up to point B, and I could get a bunch of work out of the force field that I could use to like make coffee and light the lights and stuff. And then I push it backwards along path 2, which takes less work by our assumption. We said path 2 did less work. I have to put in less work to get it back to point A. I have to put in less work than I got out of it. That means I just got some energy for free. And now what am I going to do? I'm going to do it again. And I'm going to get some more work. And I'm going to save the entire energy problem of the whole world right here. Because I have a force field which didn't take any external power, and yet it's an infinite source of energy for me. Seems pretty unlikely, doesn't it? It must be that the work done along path 1 and path 2 are the same. And it must be that the work done along any path from A to B is the same as any other path, right? Okay. Any questions?
As long as the displacement is the same, right?
As long as it's the same endpoints, A to B. Right, that's right. Good point. Yes?
If it wasn't a static force field, would the force still be the same?
Well, if I had, say, some varying magnetic field because I plugged a device into the wall, or I had one of those little desk doodads that runs off a battery, then the work wouldn't have to be the same because the extra energy that I'm getting would be coming from the battery or the wall outlet. It'd be coming from somewhere. So that's why we started with a self-contained system that doesn't have any external source of energy. And for such a system, it has to be conservative. All right, what if it were different than the energy problems the world would deal with? So now let's consider now how a force field leads to the idea of potential energy. Potential energy is kind of an imperceptible energy. If I take a brick, here's a brick. If I take a brick and I raise it, it has the ability to move things. By collision, I won't drop it that far because last time I broke something. if I, trying to find something that won't break. Here. If I drop this onto the book, it can move the book. So when I hold it up in the air, it has some power. It's got some ability, power in the loose sense, not in the strict physics sense. It has some ability to move things, either by a collision or by sticking to it. If it's stuck as well, then it would also move things. But it has some ability to move things. But when I hold it up, it's not moving. You can't see it moving. So why does it have the ability to move things? It's not warm, so it can't be like converting heat into motion. It's not lighting up. It doesn't have that kind of energy. So what is it that gives it the ability to move things? I mean, energy is, in one sense, the ability to move things. It has energy that we call potential energy. And it is the energy that we have to put into it to fight against this force field. And if we let it go, the force field gives us all that energy back. So the energy that's just waiting to be let loose, that's potential energy. Okay? Any questions? All right, so force fields lead to work and potential energy. Now I can quantify this potential energy because I know that when I put work into a force field, if I let the thing go and the force field does work back, I'm going to get back exactly the same amount of energy I put into it. Right? That's the path independence, if I let it go all the way back to the starting point. So here's a force field F, here's a particle, the force field points to the right in this example, the particle moves in the positive x direction from A to B. And we can say the work done by the field on the particle is the integral from A to B of f of x dx. And that means that the potential energy, U of B minus U of A, is equal to the negative of that. Right? Because if the field does work on the particle, it means the particle now has less potential energy. Some of that potential energy was converted into another form of energy through the process of the force field doing work on the particle. When the work on the particle is positive, the potential energy is going down. So the U final minus U initial is negative. Right? The final potential energy is less than the initial potential energy when the work done is positive. Is that clear? Now we know if I come in with my hand and I push the particle back against the force field, then the work done by the force field is going to be negative. Of course, the work done by my hand is going to be positive, but we're looking at the potential energy of the field itself. So now, here's another further question. When acted on only by the potential field, there's a graph of potential energy versus position x, and there's a particle. And we see the potential energy is low on the left and higher on the right. How does a body accelerate in such a potential energy field? Yeah. So U is a function of position, it's the potential energy as a function of position. So it's analogous to here, U of B was U of x equals B, and U of A was U of x equals A. So we're asking about potential energy of a particle when the particle is at different positions. So this argument is the position of the particle. So on this graph, what it says is, if the particle is on the left here, the potential energy is low. If the particle is on the right, the potential energy is high. So think about what happens to the potential energy if the particle moves, and if it doesn't move, and which way should the body accelerate. Okay, I'm assuming you're all popped out now, so 5 seconds. It goes down the potential hill. Yes. Because we saw earlier that when the force field acts on the particle alone, the force field is going to exert a force on the particle will accelerate in the direction of the force. If the particle starts from rest, then the particle will move in the direction of the force, and the work done by the force will be positive. So potential energy means the particle acquires kinetic energy, potential energy goes down. The potential energy of the particle was converted into kinetic energy through the process of the work done by the force field. Okay, question?
What if those, it doesn't depend on the body because this is assuming mechanics, but if you get to any electrical force and your charged particles, the scenario changes completely because about two particles which are behave differently in an electric field.
Okay, so the question is, doesn't it depend on the body? Because if we have a charged particle, then positive charges move in different directions than negative charges. And the answer is, when we're talking about potential energy, it doesn't matter because the force field works the way we described. If I were to replace U of x with V of x, which is the electric potential, which is potential energy per unit charge, then absolutely it depends on the sign of the particle. But you don't have to worry about that for another like 10 weeks or so. Okay? But that's a good question. That's a very good question. Yes, that's it.
This is graph kinetic energy. Would that just be the inverse?
Yes, excellent question. If we graph the kinetic energy, would it be the inverse? And by inverse, what we really mean is the mirror image flipped over in the plane of the screen. Right? So we have some kinetic energy, and we can flip it over. Because every joule of potential energy lost becomes a joule of kinetic energy if the particle is free, if no other forces act on it. Right? So when the potential energy goes down, the kinetic energy would be going up. So if I start this particle at rest, it will accelerate to the left, and its kinetic energy will increase even as its potential energy decreases.
Right here.
Oh yeah, thank you.
Are you
Good call.
from the graph the diagram or the graph that you show right there? Is it because the potential energy of the masses is going up, it wants to go back down?
So the question is, in this graph here, is the reason for the motion that the potential energy wants to go back down? You can kind of think of it that way. I mean, there's a common lie that people tell you all the time that says particles seek the state of minimum energy, which isn't really quite true, but they actually seek the state of minimum free energy. And so when you get, like 20 weeks from now, when you get to thermodynamics, you can learn more about that. But in this case, for energies that are large compared to thermal energies, like a baseball, then effectively it does sort of seek the state of minimum energy. But that's a consequence of what we've already said, and that's the way you can think about it, though. It's a way to remember it as well. You can also remember it as particles roll down in potential hills. I mean, if I made a graph of potential energy versus position in just gravity, then actually the graph of U of x is literally the height of some roller coaster track above the ground, because the potential energy, you may already know this, the potential energy due to gravity is mgh. And so m and g are constants for the roller coasters. And then the potential energy is proportional to the height. And so if I took a picture of the roller coaster and just projected it onto the screen, that would be the U of x curve. Yeah.
Is it technically potential energy, free energy the same? Because free energy is energy available to do work.
The question is, isn't potential energy and free energy the same? No, they're very, very different. Free energy has to do with entropy and the diffusion of heat from one system to another. It depends on the temperature. It's a much more involved concept. So potential energy is much simpler. It's very direct. It's a force field acting on a body. Yes?
If you say the potential energy, the curve of potential energy and the curve of the kinetic energy can be converted, but the graph of kinetic energy should be a curve, but the potential energy is a line, is through line.
So in this example, if the potential energy U of x looks like this, and if I have a particle that is subject to no other forces but this force field, then kinetic energy might look like this. It's simply this graph flipped over. So this would be KE. And if I follow the particle along its trajectory, as it moves to the left, its kinetic energy would be increasing. And so the KE curve here is just the U curve flipped over.
So they have the same size.
So the sum of the potential energy and the kinetic energy should always be the same. Exactly. And what's that called? The conservation of mechanical energy. In a
OMG.
conservative force field, that is always true. We'll look at that in a second.
When you
Yes.
get a number for it, I mean, look, the function is constant. It's a series of scalars.
Exactly. If we have an object, so everyone can hear. If we have an object, we let it accelerate downward, it loses potential energy.
But
So the question is, why, as we go farther to the right, does the potential energy rise? So I have invented a hypothetical potential energy. It might be, say, the potential energy of a roller coaster on a track. And the track may be higher on the right than it is on the left. And so its gravitational potential energy is higher on the right than on the left. But if I let the particles go, it won't accelerate to the right and increase its potential energy. If I let it go, the roller coaster will roll downhill. And so it will roll to the left. And its potential energy will be going down. And so it will be essentially still falling down, although guided by the track. Is that clear? Okay. Any more questions? Great. I love the questions. Great questions. Good job. Yes. Oh, okay. That's an excellent point. So what he said was, this is not a graph of a particle moving in 2 dimensions. This is a graph of a particle moving in 1 dimension. So the roller coaster thing can be a little bit confusing because, I mean, literally the projection of a roller coaster on the screen is 2-dimensional. I mean, the blackboard is 2-dimensional. But it only has 1 degree of freedom in it because it has to follow the track. And so x could be, say, the horizontal position of the track, but it's still considered 1-dimensional motion because it only takes 1 parameter, x, to define the position of the roller coaster. Okay? And it might even be simpler than that, because if this is a spring, if I have a spring, here's a spring, here's a wall, and here's my particle. When I push the particle in and compress the spring, the potential energy goes up. If I let it go and the spring expands, the potential energy goes down. And yet the motion is, in this case, purely 1-dimensional. It's just left and right. And there is no up and down, there is no roller coaster track. It's purely 1-dimensional. But it has the same graph in this sense. In that we can see that the particle will accelerate to the left by the force field. Is that clear? Okay, thank you for that. All right. Now, another academic question then. Here we have a similar situation. A force field works on a particle. The particle moves from A to B. The force field points right. How does the work done from A to B by the field on a fast-moving particle compare to the work done on a slow-moving particle? Okay, 5 seconds. So most people say it's the same. If we have a little bit more disagreement, I'm going to make you fight it out amongst yourselves. I'll hold off on that just yet. And some people say the work would be greater for a fast-moving particle. Does anybody want to elaborate on that? Why would it be greater on a fast-moving particle? Up there, great, yes.
I was actually arguing it would be the same because we can only see distance, but what would be different is not
Okay, excellent. So he says that it would be the same actually because the distance from A to B is fixed in either case. Correct me if I misquote you. And although if I made a graph of x as a function of time, I would get a different trajectory. But the displacement from A to B is the same in either case, and the force field is the same in either case. Is that correct? And therefore it should be the same. And that's exactly right. If you look at our formula for work, it turns out that time is not a factor. Time is not in here anywhere. The only thing that matters is the force of the displacement. And it doesn't matter if the displacement happens quickly or slowly. The work done for a given force over a given displacement is the same. Yes?
Maybe I feel like this is a simpler way to think of it as work done is changing kinetic energy. And even if you move it faster, the kinetic energy increases, but the change remains the same. Therefore, essentially, the changing kinetic energy let this shift upwards, but essentially, those two graphs can be projected onto each other.
Yeah, so the statement is that you can think of this as the change in kinetic energy is equal to the work done, and the change in kinetic energy is the same. And so if I had a particle, like here was a hypothetical kinetic energy curve, but I might have started out by throwing the particle, so maybe its kinetic energy started out higher. Maybe it started out here. And so this would be some kE fast as a function of that. But in going from, say, here to here, this change in kinetic energy would equal this change in kinetic energy. If my graphs are a little bit better. So it doesn't quite look it here, but is it clear what I'm trying to say here? This kinetic energy change is the same as that kinetic energy change to within experimental error. Because the work done is the same. So you can think of it that way as well. All right. Yes?
If you had said like it was accelerating faster instead of just moving faster, would it have been weird?
So the question is if it were accelerating faster. No, because the work done has nothing to do with time. No acceleration, no velocity, it's just force and displacement.